Hi, this is Steve Ward and welcome to this session on PLC system and panel design and some other related aspects around developing PLC based systems. Modern PLC based control systems have a number of requirements. Of course, you need a PLC CPU. The CPU is the item that does all of the processing and runs your IAC 61131 Part 3 programming language applications. You need I/O to interface to the plant. So I/O is inputs for all of your sensors and outputs for all of your actuators. There may be motion. For example, that could be VFDs for industrial motors. There may be servo motion. There may be stepper motors. So that's another aspect that might need considering. There may be interfaces to other devices, such as protocol converters, gateways, network switches. Some of those are related to the actual interfacing itself. But some of those devices might also be devices which actually perform part of the application control. For example, with a motion, with the VFD, you need some sort of interface to the VFD itself. There may be a local operator interface to allow the operators to understand what's going on and be able to perform control. And then we come on to the related control equipment itself. So there was a control panel or enclosure, and inside the control panel there will be terminals and glands. We also need power conditioning, power supplies, power distribution. That may include fusing and miniature circuit breakers, and possibly even the UPS if you want the PLC to continue to operate when there's no power being applied. Safety can be very important. You might need safety devices such as emergency stops and light curtains and so on. And there might need to be safety controllers which actually control what you're doing on the safety output side. And then there are environmental and regulatory considerations. So you might want to be concerned with temperature, humidity, maybe ATEX, explosive atmospheres, maybe even something like FDA 21 CFR 11 for validated environments. So all of these are aspects you need to consider for your application. To determine what PLC CPU and I/O to use, we often start with the I/O count. So this will be the number of I/O, the number of inputs and outputs, what type of inputs and outputs they are, and also the locations of those inputs and outputs. So we would consider things like the range, the accuracy, output current, isolation, and diagnostic capabilities. So for example, for a simple discrete input, we might use a 24-volt DC module. For outputs, we might use a 24-volt DC output using transistors, or maybe a relay output. For analog inputs, we might use 4 to 20 milliamps, and then we might be concerned with the accuracy. Maybe 0.5% is fine, but we might want to go to 0.1%. For analog outputs, for example, if you're sending values to a variable frequency drive, you might use 0 to 10 volts if it's a single direction with 0.1% accuracy, or for dual direction, you might want plus or minus 10 volts. For temperature inputs, you might use RTDs or thermocouples. You might want high-speed counters, and there may be pulse outputs as well. So lots of different I/O, and that will vary according to what your requirements of your particular machine or process are. Now, I/O might be local in the local CPU chassis, or there might be remote I/O. So based on what the location is and also possibly the user preference and also commercial considerations such as cost and effectiveness, you might consider Profinet, which is an Ethernet based remote I/O connection. You might consider IO-Link. IO-Link might be useful on a machine basis, particularly because you can have IO-Link interfaces which can be IP67 protected, so ideal for machine mounting without an enclosure. And there might be other considerations as well based on what equipment you're interfacing to and what available communications they have. Once you've established the I/O count, you can then start looking at your CPU choice, and this can be based on the I/O count and the application complexity. So CPUs, they vary in price. You pay more depending on what level of performance you get. Higher performance costs more money. Larger memory, data logging may also be an option. Diagnostics, but you also need to consider future expansion and of course the interface requirements we mentioned before. Has it got the right interfaces to be able to connect with those devices you need? And if not, can you add additional modules for those connections? So there might be serial, there might be Ethernet, there might be those I/O interfaces we mentioned, And the I/O interfaces, there might be a variety of different protocols you need to support. Some of those might be handled by one module. In some cases, you might need multiple modules. And it might be worth considering if you can look at alternative interfaces. It might be more expensive on an individual basis, but it might reduce the overall cost and complexity of the system to have everything running on the same network. You may need redundancy. This is usually driven by application requirements. So typically it's how much does it cost for downtime. If downtime is very expensive, then redundancy can help reduce the impact of failures, and that can allow you to reduce your downtime. And particularly with high costs of downtime, high costs for redundancy are offset by those downtime costs. But also tolerance to risk. Certain applications require higher levels of redundancy just because the users say, I don't want this to fail. So it could also be there are downstream processes which would be affected. It could be external customers would be affected, or it might be driven by internal price and operational considerations. For motion control, you would typically look at the number of axes. You look at how big is the motor for each axis. You might want to investigate the accuracy required for each axis. And of course, you'd be looking at the supply voltages. So that can include variable frequency drive. Variable frequency drive gives you support for AC motor speed control, but is otherwise relatively slow and inaccurate. But VFDs can be useful, particularly for larger motors, because they can improve efficiency overall, and that can reduce the overall cost of investment and the return on investment. So you might be paying more upfront, but the overall energy cost can be reduced, and that can reduce the cost of the system over time. Servo motors are useful for high accuracy positioning. They generally support synchronized axes movement as well, and even interpolation between different axes, so you can have high quality moves across multiple axes simultaneously. Stepper motors, also useful for high accuracy positioning, but normally using smaller motors. They can also support higher torque, and often they're open loop. So you tell a stepper motor how far to move, and it moves that distance. You don't know it has, you just assume it has based on the characteristics of the electromagnetic interfaces. And there might be linear actuators as well. They might be electric or pneumatic. Linear actuators might be used for gripping, for moving of tables. So that's another way of having motion, but often in a linear fashion rather than a rotary fashion. Now the controller will need a suitable interface to control the motor. So that could be analog outputs, or it might be communications for variable frequency drives. For servo, you typically need some sort of more advanced communications, such as EtherCAT. For a stepper motor, it's typically a simple pulse out, but the pulse out might need to be at quite high currents, so you might need a specialist stepper motor controller. And for linear actuators, that could be a simple discrete output with feedback. The feedback might even be optional. You might just use a delay to just make sure that the device has moved to where you want it to position to. But there might also be communications, and the linear actuator even might be controlled by a servo motor. So you'd look at the particular hardware you plan to use, and that would define what the control interface is. BFDs, PLCs may even have a built-in controller, or they might use Profinet or EtherCAT, etc., or there might be some modular motion controller which you might use. So again, you'd need to look at the PLC vendor to determine what the motion control capabilities are. For interfaces, you'd look at the number and type of devices you need to interface to. You'd need to look at the protocols required, and that would drive the choice of using either built-in interfaces, or maybe you need optional modules in the PLC, or you might even need external gateways depending on what's available from the PLC vendor and what's most economic for that particular application. So there is a variety of different interfaces: serial, Ethernet, Modbus. Modbus can be both serial with Modbus RTU and Ethernet with Modbus TCP. Profinet is an industrial I/O network based on Ethernet, and then there are a whole variety of additional interfaces which may be required for your application. Now in the past, most PLC applications used to be controlled by push buttons and lamps. Each push button would be wired to an input, each lamp would be wired to an output, and there would be application code that used the inputs and outputs to actually control that operator interface via these push button panels. Today we don't tend to do that. Often what you'll find is there's just maybe one or two push buttons, such as, for example, maybe an emergency stop button and a reset button, maybe a start button. Very few outputs. There might be a few lights, but very few. And generally what we rely on is a local operator interface. So the operator interface is a computer-based device with a screen, and then you would choose your local operator interface based on what size do you need in terms of screen size, what performance do you need, so how fast is the processor and how much memory does it have. Of course, what are the capabilities? Most modern interfaces are color, but maybe you only need a black and white interface. How is it going to mount? Typically it mounts in the panel itself, but you might have something that needs standalone mounting, and the mounting might define the protection. So you might have an IP66 panel at the front, but it's IP20 at the back because it goes inside the panel. But if it was freestanding, maybe you need a higher level of protection, but that's going to depend on what your application is. So for example, something that is hosed down maybe needs to be stainless steel and IP67, but something that's in quite a benign atmosphere, IP40 or 54 or something along those lines might be suitable. The operator interface might also act as a gateway or a protocol converter, so it could be a multifunction device, and it may also support local data logging or even data logging to a remote device, even up to the cloud using standard protocols like MQTT and so on. So having chosen your hardware, you can now look at what your control panel or your cabinet is going to look like, along with all the choices for terminals and glanding and so on. So the size of the PLC and I/O, that will typically drive the size of the cabinet, but you also need to consider the internal wiring and any additional components, including power supplies. Depending on the environment, you may be able to get away with a simple steel cabinet. If it's an ATEX environment, that may dictate IP54. Some applications might need stainless steel. And then you'd also need to look at requirements for the equipment in terms of its power consumption and power dissipation, because you may need fans and cooling vents and so on. Now, some I/O can interface directly to sensors and actuators, but most users prefer to use interposing terminals. And those terminals, of course, they need panel space, but they can also include fuses and disconnects, which can simplify maintenance and testing and configuration of the final connection to the I/O devices. Some industries also demand additional cross-connection cabinets. So you have your cabinet with your PLC, and then you'll have another cabinet next to it, which is just full of these cross-connection terminals. It certainly gives you more flexibility, but of course it costs a lot more. It's additional wiring, it's additional installation. So you have to decide if that's worth it for you and if it's your industry standard or not. Cabinets may need to be segregated. You might have bus bars and high voltage in one part of a cabinet or panel. You might put high temperature devices at the top so that the heat rises and doesn't affect other devices. You often need to consider separating powerful devices or that use a lot of power from signal level devices. And you may also need to separate safe and non-safe zones, particularly if you've got a safety related application. It's also worth considering the panel space you use and allowing for spare panel space and also spare I/O modules to allow for simple future expansion. If you make everything too small, then of course you might save money initially, but you could make any future upgrades very expensive and difficult, even to the extent that you might have to replace the whole panel in future if you want to do any sort of upgrade. Now I have a separate session on power supplies, but briefly, you also need to consider power conditioning. Power conditioning is how you handle the mains input, and does it need any special regulation? Maybe you need some sort of constant voltage transformer or some sort of choke which can manage the input power. You need power supplies because modern computers and electronics typically run off 24 volt DC rather than the 110 or 240 volt mains inputs. And then you need to think about how you distribute your power to the different components. So this will be based on what is your mains power supply, what is its quality, and of course by the application requirements itself. Fuses and MCBs are as required by the application and user preference. So you typically need at least one fuse or MCB per power supply. You may need one per device. You might have a fuse or MCB per I/O group, and you may even go down to one fuse or MCB per I/O circuit. Of course, the more fuses and MCBs you have, the more expensive the wiring and the more costs there are, but that could ease fault finding and it could improve your capabilities to survive issues in future. So you can also offset the initial costs against that return on investment. So looking at these diagrams, we typically see a single power supply which comes in to your system devices. So that would include power to the operator interface and the power to the CPU. Normally that's a separate power supply because that's quite a clean supply which is required by these electronic devices. We would then have an additional power supply for the inputs. So this would be a relatively low powered power supply because normally the inputs don't need that much power. So the input supply might power your input modules, your I/O modules. It might provide the 24 volts to your input devices, such as limit switches and proximity switches, and that would be wired to your actual input modules. And you would size that power supply based on what is your input device capability, plus some spare capacity as well. And then we usually have a separate output power supply. The reason for this is the outputs are often much higher current and also a lot noisier in terms of the electromagnetics that are generated by electromagnetic devices like relays and contactors and so on. So the other reason is, of course, if you have separate supplies, you're avoiding electrical noise that avoids affecting the circuitry, and it also gives you additional protection as well in case of an overload on the single power supply. So on the output power supply, this is typically a larger power supply, supplying power to the output module, which in turn supplies power to the output devices. So there's a variety of calculations you would use to determine the size of these power supplies based on the consumption of the modules, the consumption of the devices, the amount of power that each input device might take, and of course, the amount of power that each output device takes. But also you need to think about simultaneity as well. How many of these devices are actually powered up at once? For example, in pneumatic applications, it's typical to find each pneumatic cylinder has two outputs, but only one of those outputs is on at any one time. So there's one to extend, one to retract. It's rare that both of those will be on at the same time. So here's an example panel layout for a typical PLC application. Looking at the front view, we normally have power conditioning and power supplies along with the main master circuit breaker or miniature circuit breaker and fuses at the top. One of the reasons for doing this is power supplies can generate quite a lot of heat. So by having these at the top, that can allow that heat to flow to the top of the panel and avoid affecting other devices beneath, which may generate less heat, but which in turn also may be heat sensitive. There would then be a variety of cable trunking to allow us to manage all of the different cables. We might want to segregate the different trunking so that we avoid running high powered circuits along with signal level circuits. And then we also might want to segregate low voltage and high voltage, low current, high current. We might want to segregate communications. We might want to segregate various different categories depending on what we think the possibilities for noise would be. But there's certainly going to be a need for some sort of cable trunking running around the panel to distribute all the wires. So the next level we might see, moving down the panel, is the PLC, the I/O and other devices. These are typically the industrial electronic type components, including the ones that actually do the control along with the interfacing. Underneath that we might find I/O terminals. These don't generate any heat generally. The I/O terminals are used to connect the I/O interface to the actual I/O wiring that comes in from the outside field. And again, that will be wired via glands and then through suitable cable trunking. And then you might put very heavy items at the bottom of the panel, mainly because it improves the stability of your panel. If you've got heavy items like transformers and drives at the bottom, yes, they will be generating some heat, which could be problematic. So you might need to think about ventilation and even fans. But if you put those heavy items at the bottom, then it means the panel can be more stable and less likely to tip over. So often those go at the bottom. And of course, that also helps from a physical mounting point of view. You don't have to lift them up very high to be able to install them. And you can see what this looks like on the left side view as well. So the trunking is often narrower and shorter than the other components, and that gives you space for wiring. And you also need to think about access around all of the devices. Is there actually physical space to get your fingers in to do the wiring? Is there space for expansion? And is there space for heat dissipation, which will come from the vendor's instructions? So there's quite a few considerations as to how we actually build this panel layout. Now you need to consider safety. Again, I've got a separate session on safety standards, but at a very high level, you typically need to look at the functional safety requirements for your application, and that's often produced by performing a HAZOP, or a hazardous operational review, or some sort of functional safety review, or some sort of investigation of, is this machine or process requiring of particular safety. Now that HAZOP and functional safety review should be performed by someone that has the relevant safety standards and education. It could also be supplemented by people who maybe aren't familiar with the safety regulations, but ultimately safety is the responsibility of the end user, and they should take a suitable approach in order to make sure that the system is safe and that users are protected from unsafe applications and unsafe operations. Safety can also extend for certain applications beyond the operators. You might be looking at applications which could have the potential to affect the environment, and there could even be larger safety implications there. So again, you need the right people performing the functional safety review to make sure that it is performed effectively. Now, in a typical process, there's really two types of safety. Machine safety under EN ISO 13849 typically includes safety relays and safety controllers. There may also be safety devices such as light curtains, pressure sensors and guard locks. But the idea of machine safety, it's normally about high operations, high numbers of operations and fast response. So if you've got an operator who's loading a machine, they could be loading the machine every few minutes. You need to have appropriate safety to stop the machine from operating while they're loading the machine to avoid any physical injury from the machine operating. And they could be loading the machine quite frequently, unloading the machine quite frequently. And that can also include guarding on cells, guarding on any entry into the cell itself. Also maybe that could extend to things like robot safety and so on. But the idea is it's safety that needs to operate quite quickly to stop injury to an operator, but also has to operate quite frequently. The opposite of process safety applies to the particular processes, often where you're making stuff rather than things, and the standard that applies is IEC 61508. With process safety, they are normally a lot slower. It can be a few seconds for them to operate because you don't want spurious trips. But also it might be that the safety doesn't operate very frequently. You might test the process safety system once a year, but you might find in the real world the process safety system never actually operates. It's almost like an insurance policy. You hope you never need to call on it. So the idea of process safety is you're preventing injury to operators, but you're also preventing damage to the environment as well. But they are generally required a lot less. So we might be looking at emergency shutdown to stop a process application from operating. We might be looking at a fire and gas suppression system that operates when there's a fire. So hopefully we'll never need to do an emergency shutdown. Hopefully there will never need to be operation to prevent a fire or gas leak, but you need that safety system there just in case. So process safety can also require a separate safety instrumented system, whereas machine safety might be integrated into the PLC or have a local safety controller. The safety instrumented system under the various safety standards doesn't just include the system itself, but it also includes any safety sensors and actuators, and there's other standards that cover that, including IEC 61511. So again, you need to have the right people involved to make sure your system is safe. And there are additional safety measures which are out of the scope of the control system, which could include operator training. That might include passive safety. For example, in hydrogen systems, we see that they're open to the air to allow hydrogen to dissipate into the atmosphere. We might have high level safety functions like a high integrity protection system, like a high level emergency stop system that just cuts power to everything. And there might be other safety functions there as well. Including, for example, with fire protection, you might have regular fire patrols by a person who's trained in putting out fires using appropriate fire extinguishers. So outside the scope of the control system, but still required for the overall fire safety. Separately, you should also consider electrical safety. Typically, anything over about 24 volts is an electric shock risk, and you need to make sure that operators and users are protected from high voltages. 24 volts is fine, but yeah, anything over about 40 volts could potentially cause a shock. 110 volts can be caused quite a painful shock. 230 volts and above can even be fatal. So yeah, electrical safety is very important as well, but separate from this HAZOP or functional safety. Then there are environmental and regulatory concerns. So we need to consider temperature and humidity. It may be our control system is quite happy with 0 to 60 degrees and 5 to 95% humidity, which is pretty much the standard under IEC 61131 Part 2. But there may be higher or lower temperatures that you need to cope with. There might be explosive atmospheres, which is where ATEX and IEC EX comes in. You might also have corrosive atmospheres, for example, hydrogen sulfide, or maybe you've got a lot of salt spray. And all of this will depend on what the application is, and the application itself may have its own particular requirements as well. So you would choose components and design the system accordingly. For example, for explosive atmospheres, you may need something that is ATEX Zone 2 compatible. You might even need to go to ATEX Zone 1, and that might involve the use of intrinsic safety. Intrinsic safety is often using barriers which prevent a dangerous voltage and current getting out into the field and prevents the possibility of having a spark that might ignite an explosive environment. You might also need cooling for heat, so that could be active cooling as well as the temperature and humidity ratings for the equipment. You might need shading if it's outside, particularly some sort of shading to prevent direct sunlight. Conformal coating can help against corrosive atmospheres. And I mentioned ATEX. ATEX is mandatory for explosive atmospheres. And again, that's got its own level of safety, and you need competent people in order to understand these explosive atmosphere requirements. FDA 21 CFR 11 is slightly different. This is often covering particular requirements for traceability and recordability. So that doesn't necessarily affect your design as much, but it might affect your choice of components, and it might affect how you develop the application, because you need to record everything you've done, and you also need, when the application is running, to record everything that the operators do as well. So yeah, these regulatory compliance might also have an impact on the overall system, maybe at a higher level though than the particular component choice. So here's an example system architecture. I'm not showing the power supply arrangement here, but what you'd have is, in the middle, the core of your system is your CPU. The PLC CPU runs your IEC 61131 Part 3 languages and possibly performs additional functions depending on the capabilities of the CPU. It would also have suitable interfaces. So here I've got probably an Ethernet interface to an operator interface. The operator interface would allow the operator to understand what the machine is doing and also to control the machine by performing set points and by emulating push buttons on the screen to allow the operator to start and stop the machine. There might also then be an Ethernet connection to the remote I/O, so that could be Profinet or Ethernet IP or some similar network. And then we'd have our remote I/O drops which sit on that Ethernet network, and they would be distributed around the machine or process, and they would interface with the exact I/O devices. And then here we've also got a safety application. So the safety application is supervised by the CPU, but it runs independently, and the safety application has its own I/O that allows you to safely shut down the system depending on what your requirements are. Again, referring back to either is it machine safety or is it process safety, or what is it? And then there may be additional interfaces, for example, Ethernet to intelligent transmitters or to other devices, or maybe up to high level systems. So once you've gathered the requirements, here is the suggested development process. So you'd start by creating a bill of materials, and from that you can create the architecture, or maybe the other way around. Maybe you create the architecture first and develop the bill of materials from that. But they're very much processes that go alongside, and that's generally based on the I/O count. You can then refine that bill of material to include power supplies, fuses, and extra components as required. And then what you would do is you would move on to create line diagrams and schematics, which would give you better definition of what the wiring details would be. So for example, it's all very well to show a single line connection to an input device, But ultimately you need to define how is that input device wired. Is it 2-wire, 3-wire? Do you need a positive supply? Does it just need a single wire to the I/O? Do you need grounding and earthing and so on? So there's a lot of details that might be required when you actually start working on these schematics. You then calculate the space requirements. That defines the panel space required. In practice, you usually have a defined panel space and you have to make the components fit. But you also might find that the components won't fit and you have to go up to a bigger panel design. So that panel, you might have some constraints there, but ultimately if the components can't fit, you will need more panel space, possibly going to 2 panels or a bigger panel. And then you would create the detailed design drawings. This is typically done using a CAD package, computer-aided design, and you would use the appropriate standards for the drawings based on whatever your standards you want to use are. At this stage, you can also define the precise wiring, including wire numbers. And this is also where you might define earthing, fusing, cooling and airflow and voltage separation. They also might be defined at this stage. For the project itself, you get multiple documentation requirements. You might not need all of these, depends on the application. So often you'll get some sort of requirements from the client. That may extend to a user requirement specification. The user requirement specification is a detailed document that defines exactly what the user wants, but doesn't explain how it will be implemented. So it's a good level of specification from the user to indicate to the vendor what they need to supply in terms of how the system will operate finally. And it may also include details about testing. It might include details about panel protection and capabilities, and even down to the color and thickness of paint and so on, but normally at the very high user level. There may be a functional design specification. The functional design specification is the next level document that describes the function of the system and how it will operate. So this might include details of sequences, it might include more details of the particular interfaces, and it might even go into some details of how the user interface and the user experience might look. So user requirement specification might come from the client, or it might be part of the project requirements. Functional design specification is normally developed by the panel builder because this describes how they will actually implement the requirements in the user requirement specification. From the functional design specification, you can then choose to create a hardware design specification and a software design specification. So these two documents go into more detail to cover how the hardware will be constructed and how the software will be developed, respectively. There may also be test specifications along with results. So that might include test specifications for the factory acceptance testing. There might also be site acceptance testing. And if you're in life sciences projects with 21 CFR 11 requirements, there may be many more documents. And also for safety systems as well, there might be many more documents you need to fill in, such as HAZOP, LOPA, SIL review documents, and so on. Then you have your drawings. You'll have your design drawings, which is what you plan to build. But you might find when you're actually building the system, some things don't fit. So you might also want then to draw your as-built drawings, which will be actually supplied for the system. And then there might be user manuals which explain to the operator how the system will work. And then there may be additional regulatory documents that you have to complete, for example, ATEX. There may be related documents for declaration of conformity and restriction of hazardous substances. There might be safety documents and so on. So all of these are aspects that you need to consider in order to build your application. And that gives you an idea of all the steps that are required and the sorts of documentation that you'll ultimately create to describe the system.